let's take a look at the chapter 2's homework. Please just practice it, okay? I hope you can practice all of them. If not, at least practice some, okay? So I think I posted, I think about a week ago. Did anybody even look at it or tried it? And do you have any questions at this moment? If you have a question, I can answer it now, I think, yeah.
I'll probably have questions next week. My book just came in, I think yesterday.
Oh, okay, okay. No problem, no problem. I won't give you a quiz today, okay? But probably I will give you a quiz next week, maybe one quiz problem next week. Tuesday we don't have class, so Thursday, okay, probably we have a quiz about chapter 2. Not necessarily the homework problems, but it might be very similar. Okay, so I guess so I will suggest you prepare it. Okay. Let's look at a couple problems on the homework. Okay. So one of the topic, let's say review of. I'll give you a review. How about that? Every chapter I give you a review.
You gonna share your screen?
Oh, I haven't checked my screen. Okay, let me share. I did click the record, but I didn't click share screen, right? Okay. Here we go. Okay, you see it?
Yep, it's there.
Good. Let me now start from now. Let me give you a review for every chapter. You know, when we finish the chapter, let's do a quick review, and maybe that will be beneficial to you. Okay. Chapter 2, a couple content. I think it's testable. You know, I'm on the same boat as you. When I was a student, I learned stuff. I study toward the test. You know, if it's possible, it could be on the test, I will study. I'll try to learn it. Okay, it's okay. It doesn't matter. Life is a test, so we prepare for the test, right? So I think a couple topics that could be on the test. Okay, so other than those, actually found the basic properties you need to know, right? When you solve a problem, of course you need to know those properties. Okay, like gamma, like gamma is what, specific weight, right, and a specific gravity. Of course, density you need to know, right? Those properties, of course, you need to know. But for the testing point, I think that viscosity is definitely a testing point. Okay, so think about, if you are in my shoe, if you give students a test, you want to try to test them viscosity, the content. What kind of problem can you can use to test? If I give you an exam or something, it has to be, think about it. It has to be this equation. Otherwise, how do I test you, right? Right. So any problem, if I want to test you this topic, I will give you a problem to solve using this equation. Okay, that makes sense? Okay, so you fully understand this equation. So look at the homework problem. So I have a couple problems, different type of problems that are using this equation. For example, I can share with you what, let's say, I don't know if I assigned a problem 2.33. Let's just use that. Let's see, you have a velocity. They give you a velocity profile, okay? So you have to get familiar with the form, function of velocity, right? Okay. What is that? This is the flow between two parallel plates.
Is that M for mu?
Yeah, it's mu. Well, we're talking about viscosity, right? Same viscosity here, right? So it must be viscosity. It's a property. Okay. So that's between two parallel plates. Okay. The plate, you have a distance B. You have flow in between. Okay, I think the flow look like this. Parabolic shape of the velocity profile. That's why mathematically we can describe this shape using this function. Okay, that's basically the background of this problem. First of all, do you understand the problem statement here? Fully understand? Before we continue, otherwise if I continue, then you have no clue. Okay, so this is the y-axis, right? This is the u velocity. Okay, when it goes into these two parallel plates, you go flow in between these two parallel plates, velocity profile will be like this. Okay, this is 2.33. That's one of the textbook homework problem, right? Okay, so look at the function. Okay, you're an engineer. If you get a degree, you really need to know good on math, right? You have to understand those meaning of those math expressions. So it says, hey, the velocity change with basically with y. See, by minus y squared, right? It's a parabolic shape. It must be like this. Okay. Mu is a viscosity constant. Doesn't matter. What is dp dx? You often will see dp dx in problems. dp dx is the pressure drop, the pressure gradient along the x direction. Okay, let's think about the nature of the problem. So if there's a flow between the two plates, what drives the flow? What do you need energy to make the fluid flowing, right? You need energy. You need a pump power. Okay, in reality, otherwise the fluid just stay there stationary if you don't give power. Is that right? So dp dx means pressure gradient. So pressure will drop, okay, along the flow direction. Do you agree? In any pipe, the pressure will gradually drop. Well, why is that? Why pressure will drop? Pressure represents the form of energy here in this system, right? So the energy is being taken to convert into the movement of the fluid. Of course, pressure is going to drop. That makes sense? That makes sense? Everybody, please understand the concept, the physics, right? So I'm trying to explain to bridge a problem in textbook to a reality. Okay, so for you to for you to easily understand. Okay. So let me ask you this: the dp dx, you know, this is a calculus 1, right? You should know what's the meaning of dp dx. Just like in the last example we did, the oil film thickness, will you du dy. So dp dx physical meaning, same thing, right? Delta p over delta x. If you have a small delta x, the pressure changes a little bit along that x direction. So that's dp dx. Okay, so let me ask you this. In reality, is dp dx positive or negative? From common sense, from your experience, life experience, whatever.
Negative.
It should be negative, right? Everybody agree? It should be negative because pressure always decreases along the x direction. Let's assume x direction is the flow direction, right? So it's always decreases. So dp dx is always downstream pressure minus upstream pressure divided by delta x distance, okay, in between. So the pressure decreases, so the downstream pressure is less than the upstream pressure. That's why dp dx is always negative in reality. Okay, okay, just for your information. Okay. Okay, so this equation here, this actually is a problem statement, describe the flow, the velocity inside, in between these two plates is changes. I don't know, okay? So it changes only with y. In other words, it doesn't change with x. So in other words, it's fully developed. In any location, you draw a profile, vertical profile, on any location of in between, you have the same velocity profile, because from this expression, you can see that velocity only changes with y. Don't worry about the dpdx. This is a constant. Okay, so it's a value. So usually you need to supply to the system to make the fluid move. Okay, so we assume this is the constant. Then the velocity is the function of y only. Okay, we think this problem. So what is the shear stress? Okay, I guess that's the problem. I don't want to read the detail, but I don't want to give you exactly the answer. So, but I just want to talk about it. So I think the problem asks you to calculate the shear stress. Let's say shear stress along the bottom wall. First of all, physically, do you know that there's a shear stress there on the wall? If you are, and let's say, if you are the surface of the bottom wall, what do you feel? If you lay down on the wall, upside, facing up, okay, your face, the fluid will just go across your face, okay? Let's say like that, okay? What do you feel? Do you feel anything from the fluid moving through your face? You feel the shear. Okay, so that's exactly what the problem wants you to calculate. How much shear stress you feel. Okay, so I want to add also one more thing. So it's shear stress is an action reaction between the two mediums, two materials. So your surface, your fluid apply a shear to the surface. But that's the action reaction. If you are the fluid, how about you are the fluid? You're facing down, your face down to the surface. You're the fluid, okay? You're moving forward. Do you feel anything from the surface? You see, action reaction, right? I see you nod your head, Daniel. Yeah, I feel you understand, right? So you feel that shear stress, shear force from the wall, okay? Right? So that's an action reaction. That's exactly same force, same magnitude. But depend on which one you look at. You want to calculate the shear to the fluid, or you want to calculate the shear to the wall. The magnitude are the same, but the signs are different. They will have opposite sign, depend on you are looking at the fluid or look at the surface. Okay, that's a confusing point. Sometimes you see the equation shear, you have a minus sign in front of it. See, this equation could be negative or could be positive. It's okay. Either way is right. Depend on the shear to the fluid or the shear to the wall. Okay, the sign is just tell the direction. Depend on the object, which really you want to look at. Okay, the important part is the magnitude of the shear. Okay, for this problem. That makes sense, everybody? Okay, I think so. I learned this whole thing also from undergraduate, from graduate school. That's my problem. That was my problem when I always see some book is that negative, some book is positive for the shear. At that time, I was confused. Okay, nobody taught me that. The teacher didn't pay attention to that. They thought everybody know that. I didn't. I confused for a while. Now I understand. I have to teach. Then I understand. Okay, so okay, be careful the sign. Okay, now shear stress. What's the process to calculating shear stress at the bottom? Okay, at the bottom, what is the y? At y equal to what? Let's say this is the origin of y-axis. How about that? Let's make the problem easy. This is the origin, bottom surface. So going up vertical axis is y. Okay. So what is the y value here on the bottom surface?
0.
Yeah. Yeah, it is 0. Okay. So what is the process? I give you a multiple choice to make. Okay. You can substitute the y 0 into this equation velocity expression first to calculate the velocity, then try to calculate the shear. Or you doing the derivative first to calculate the shear without knowing y value, then substitute the y value afterward. So which method, which route do you want to go? Or which one is right? You want to substitute the y first, or you want to do the derivative first? Okay, but first of all, you need to know that you want to use this equation. They have the du dy there, so you have to do derivative, right? Either way, you have to do derivative. You have a u expression, so you can do derivative. You can challenge your math a little bit, but you have to. Okay, or you just substitute the y value into the u, then get the u value here, then take a derivative. Which one you want to go? Now, if you do derivative first, then after you take a derivative, after you calculate the tau, then you need to substitute y equal to 0 there to find the actual shear stress value, right? So which route do you want to go? I need some answer from you.
Probably need to do the derivative first, right?
That's absolutely right. You have to. The other way is the common mistake students always make. Okay, you can substitute the value. You cannot before you do derivative. So let's take a look. What if you substitute y equal to 0 in this equation? What is the u value when you substitute y there?
0.
U equals 0. Yeah, sure. That makes sense, right? On the wall, velocity is 0. We know it. Okay. But after you get u equal to 0, can you take a derivative, then calculate the shear? What is the shear then? Then become a 0 shear. d0 dy. You can't do that, right? Okay. Then the shear, obviously that's wrong. You know that the shear. Okay, the shear is not 0. So in that sense, you cannot substitute the value first before you do derivative. That's the rule of thumb. Always, you have to do derivative. You have to choose the hard route. I know, substitute y equal to 0 in there, then make life much easier. Hey, everything's 0. But that's wrong, okay? You choose the difficult one. So you take derivative respect to y first times the viscosity. Then after you take derivative, you see there's still that y there. See, this is by minus y squared, right? What is it take derivative with respect to y? It will be b minus 2y. Okay, so you still have an expression in terms of y there. Then you substitute y equal to 0 there. Let's see what the value will be. Okay, so I'm not gonna do that. I'm just show you that's the correct way to do. Be careful. Okay, that makes sense. Any questions? I think there's another problem that you 2.36, that one I remember we definitely assigned. Totally, that give you a longer form, longer expression for you. Basically, it's longer than this. Still the same thing. You're gonna take derivative respect to y, okay? Then substitute the value. Substitute the value of y, okay? So in that sense, if you pay attention to this, you know actually at every y value, every y location, every vertical location, you will have a shear stress. Okay, it's not only shear stress to the wall, in between the fluid particles, in between the fluid layers, you also have the shear in between them. You think about this layer by layer, horizontal layers of fluid, you know? Each different layer, because they have different velocity, they have actually shear between each other. So any location, there is a shear. Okay, there is shear. So educated guess, where is the maximum shear and where is the minimal shear inside of this fluid vertically? Maximum shear stress, where is it? Or and minimum shear stress, where is it?
The maximum is probably at the edges and the minimum is at the center.
Or why is that? you
Because
tell
you
me
have the most
the-
resistance coming from the walls at the edges, right? And I would say it sort of decreases the closer you get to the middle. The
What
layers.
what decreases again?
The pressure, or no, the shear force, shear stress. I'm sorry, shear.
How do you know the shear force decreases?
I'm taking a shot in the dark here. That's just what my gut tells me.
Okay, so you're good. And that's really a good educated guess. Actually, it's correct. What you answer is correct, but the reasoning part is not. Okay.
Oh, okay.
Okay. The idea, the thing I want to convey here as an engineering and as an engineering professor to engineering student is always use your equation to prove your outcome. Okay. Always. Math is your tool, your equation. Don't believe your, how to say, intuition or something like that. It might not be right. Your intuition might be right, you know, but for engineering work, it's serious. You need to sign your name there. So it's better to be 100% right, okay? So a good habit is don't say until you, don't tell people anything until you 100% sure you're right, okay? Because your reputation is on the line, everything is like that, right? Even people are gonna sue you, you know, if something fell, you know, you're in trouble. So you have your responsibility. So everything you can rely on the God of the Bible is the equation, because people prove to you it's the right. So here we have only one equation here. From looking at the equation, can you tell which location has the higher shear or which location has the lower shear? By the equation, you stick with your equation. The equation is to calculate the shear on every different locations of the fluid, right? So this shear equation, what does it tell you? Okay, you see, viscosity here is a property, it won't change. The shear equal to this basically two things together, right? Viscosity and the du dy. Viscosity, nothing, no fancy, nothing there. It's just a property, it's a value, okay, constant. Okay, so your shear only related to the du dy. So if du dy is a maximum, your shear is a maximum, vice versa. If your du dy is minimal, your shear is minimal. Is that right? So that's a clue, that's a direction you want to go. So now look at the shape of your velocity profile down there. In which location the du dy is minimal? Is the shape here representing du dy? The change of velocity along y direction, see? Okay, it requires a little bit calculus now, right? The minimum point is in the middle, du dy. Why is it there? Du dy, you know, right? Du dy is the gradient. Here, what is the gradient? Tangential, right? In calculus, you know, this du dy representing the tangential of the curve, right? Here in the top tip, on that location, the gradient is 0, no change of velocity. Your tangential is a vertical line. That means the du dy is 0. Is that right? Is that what we learned in calculus? some of you may forget. Okay, but it's very important. Calculus actually serve a purpose. It's not like a fancy subject it's really, really helpful, okay, for engineers. Okay, that's why now you know, okay, in the middle of the fluid, actually du dy is 0. So your shear is 0 in there. It's a minimum point. Okay, minimum shear point. So the maximum shear point will be on the wall, because that tangential is the largest, right? Then your du dy is largest over there along this shape, along this curve. So definitely in the wall, you have a maximum shear stress. Okay. Same thing on the top wall, same, right? It's just the opposite direction, but also the maximum du dy on the wall. Okay. Okay, so that's I want to convey. So one topic, shear stress problem. Okay, shear stress is this. The other part of a shear stress problem, just like example problem we did, physical problem. Okay, you have a problem like this, it moves. Okay, so you can relate your shear stress to the movement, to the velocity. Velocity is in here. Okay, so I think there's a couple other problems like that, similar, like for example, 2.37, okay, on the textbook. That's similar to the procedure, the way you solve it will be similar to what we did in class, right? That example problem. Okay, So basically try to calculate the force and related the force to the velocity, to the movement, using this equation, because du dy actually tell you something about the velocity. If the film is thin, so basically it's just one velocity minus the other velocity divided by the distance. Okay, that good? So for the viscosity topic, these are the only problem it's possible I can think of if I test you. Okay, okay. When you prepare something, you also think as I think. How can I test you, right? Then you prepare it. So then you can prepare one. Okay. So this is the viscosity topic. Then surface tension topic, right? These are the only two topics it's possible for me to test you. Like vapor pressure, those kind of things, it's difficult for me to give you a problem to test because then become a total like kind of a thermodynamics problem, right? I don't really like to. So surface tension is another topic. It's possible I test you. So do you have any equation for surface tension? See, the content it's possible for me to test you must have the equation associated with that content. Otherwise, it's hard for me to give you a problem to test. Okay, so in a sense, you need to remember this second equation. Surface tension, you have surface tension force, right? Sigma equals to sigma times a length. That equation is simple too. But again, you have to fully understand the meaning of this equation. Like I think we have two examples in the class. Two examples, right? For the droplet, if it breaks, it breaks along the center line, a circle, okay, on the surface. Okay, if the capillary effect, surface tension is on the wall, going up, right? Pull the liquid up. So surface tension problem could be kind of difficult because I think the most difficult part of solving surface tension problem is to identify, I want to write this down. Identify what? Identify the interface between your liquid and the air, or between your liquid and the solid. There's the interface there. The reason you need to identify the interface is you need to apply your surface tension force on that interface. Okay, think about the free body diagram, right? If you don't even know where the interface is, how the heck could you even draw a free body diagram, right? It's a starting point. Otherwise, you don't have a free body diagram, it's really difficult for you to solve a problem. Okay, so interface, where is it? Okay, so it's a water line. Basically, if it's a liquid in the air interface, it must be is that water line. Okay, if there's a solid object in the water, there's a water line, right? The water line is the interface. Your surface tension force will be on there. Okay, so I think I suggest you really spend some time to look at the surface tension homework problems. We already did the two examples. The homework problem is really, fancy to me. It's difficult to think about how to solve the problem. For example, that dragonfly problem. I don't know if you ever already seen it. 2.59, right? The dragonfly. The dragonfly can stand on the water. What? It's not possible. How can you stand on the water? Why it's not sinking? Why it's not sink? Okay, so think about it. When the 6 legs of that dragonfly stand on the water, okay, each leg has a water line, right? It's not sinking, it's just pulling down the water. The surface tension can sustain the weight of the dragonfly. So you have to identify the water line on each leg. I think the leg is like, each leg is like a cylinder. It's a cylinder, sit on the water. Okay, if it's a cylinder, where is the water line? Okay, identify that, you should be able to calculate the length of the water line. See, you have to have an L in this equation. So some of the task here is just to find out the length of that water line for surface tension problem. Again, the sigma is a property. It doesn't matter. It's just a constant. So for this type of problem, I think the goal is to find the length. So you need to identify that water line. Then you can calculate the length. Okay. Okay, I'm all talk about the problem solving. Okay, so there are a couple problems like 2.67. It seems like a tricky, but hey, if you can identify the water line, you know the surface tension force. That's a big part of the problem there. Okay. Is that good, everybody? Good, right? I think it helpful for you to, for the homework problems. So now I think you should be able to solve those problems I assigned. Okay. Then prepare a good, we have a quiz next week, maybe next Thursday. So yeah, prepare for it. Okay. Any questions here? I want everybody to ace the quiz, just like the first one. Most of you, not everybody. most of you. So you can, right? In my class, my reputation, I know usually it's a C, average C class in 311, right? It's difficult, that thing is very much difficult. I'd rather take it in the summer. Everybody get an A. I know everything you guys talk about, but see, but in my heart, I truly want everybody, once in my lifetime, I want to see entire class get an A, That means I teach really well. I conveyed my idea. Okay, so I just trying. Okay, I have the same goal as you, basically. Just trying to say.
Or you could just be nice and give us an all.
No, I don't want to do that. That's against my principle, Okay, so follow this. Okay, practice a little bit. You should be good. Okay, so that's my suggestion. Okay, let's move on to. But before we move on to chapter 3, any questions here?
Are you going to post the answers to the homework problems so we know if we got it right or wrong?
Probably not. You know what? Because I will choose some of the homework problem possibly for the quiz. So if you want to know, we can talk. You can chat with me. I'll give you an answer, but I don't want to just publicly post everything. So, but after the quiz, I will post the solution. For those problems. I use as a quiz. Okay. Okay. Yep. Let's move on to. I saved it. Let's create a new note. 10 page. I will post the chapter 2's notes later. I saved it already. So chapter 3 we'll start a new note. Okay. Okay, what is chapter 3? Hydrostatic. Chapter 3 is a very important chapter. Okay, we're gonna spend several weeks on there. That's the only chapter for the statics, fluid statics in the entire semester, in the entire textbook. Okay, so usually, the 201, 202, you spend the whole semester on 201, then a whole semester on 202, right? Statics and dynamics. Here, we put it into one semester. So chapter 3 is a place for the statics. Okay, so the thing I want to introduce here is the pressure, right? Pressure. Well, let's talk a little bit about pressure. And I'm going to extensively use pressure for solving a lot of problems. Okay. Pressure, the definition. That's what everybody know, right? If you have passed the high school physics or maybe college physics, pressure is force times area. Okay, but this equation is not always true. First of all, let me introduce the unit here. Unit is Newton per area, right? Newton per meter square. So we give a name called Pascal. Pascal, okay, PA. That's the unit of pressure. It's equivalent to Newton per meter square. Okay, so it's same thing, just give a name. You don't want to write Newton per meter square all the time. PA is easier to write. Okay, that's the SI unit, but how about English unit? you probably will say PSI, right? PSI is very commonly used, but actually in the calculation, in all the calculation, it will be PSF directly from the calculation. So you have to convert into PSI if you decide to use PSI. Okay, PSF is the standard pressure unit for fluids. Okay, pound per square foot. Okay, so can you convert PSF to PSI? What is the conversion here? Divided by or multiplied by? PSF is bigger value, right? Then you have to divide it by 144, right? Become PSI, 12 square, okay? So that's how you convert it into PSI. Okay. So let's come back to this equation. This equation has a big assumption here, it's a big condition. The pressure has to be uniform on the surface. Okay, pressure uniform. Hey, we use the uniform, this word a lot, right? Uniform velocity. Now pressure, uniform pressure. What does that mean? Uniform surface, you know, uniform pressure on a surface. For example, you see, I have a paper, all right? Note here, okay? If I put my paper horizontal on here like this, okay? So the pressure on the paper surface is uniform. Okay, because pressure changes with elevation, right? You have atmospheric pressure on it. Although you don't feel much, but actually there's the pressure on it, right? On the surface. So force times divided by area is your pressure. So uniform pressure means, you know, it's a horizontal plane, okay? And the forces evenly distributed on it, then the pressure is uniform. With that, you can use this equation, P equal to F divided by A, sure. But what if pressure is not uniform on the surface? It's possible, right? It's possible, even like this, hey, I turn the paper with an angle. Some points are lower, some points are higher. Okay, maybe I put this plate underwater, okay? So some point is higher, some point is lower, for example. Okay, this is the plate. I put it underwater. Now you see, okay, the pressure on this surface in the lower point, in the higher point, of course, they are different. Right? Did everybody remember that pressure change with elevation only? Right? How to calculate pressure? Rho GH, remember that? In physics? Rho GH. So H is the water depth, right? So on any point, you should be able to calculate the pressure, right? Depending on the H. Is that right? Okay. So in that sense, this pressure is non-uniform on this surface. Okay, it's non-uniform. So the non-uniform pressure, then you don't have a equation to calculate the pressure. You know? So what is the pressure on this surface? I don't know. It changes from this to that. Okay, of course, even if you know what the force, hey, I can have a force meter here to measure the force the plate experience. Okay, so what? The force, okay, I got the force, then divided by the area. No, that's so-called average pressure. Sure, average pressure, it is like this still. But I have no way to know the location. Each location has, no, it's not, right? It's have different pressure values. Okay, so if it's non-uniform pressure situation, your local P, any given P is, we'll have to use calculus, right? dFdA, right? It's a derivative. Okay. Hey, by the way, do you understand actually the meaning of the dFdA? dFdA, you can equivalent to delta F, delta A, right? Take a limit, that will be equal, right? If delta A is infinitely small, they are equal, right? You take a limit, basically. If you take a limit, they are equal, okay? But if you don't have a limit for any application, you always can have df and dA. What do you mean by dA? Okay, I have a small element on the plate. Let's say this is called delta A. Okay, I can measure the force on this element. That's called delta F. Let's assume the pressure on this small element is the same. It's not, but let's assume it's same, approximate. Okay, if the element is small enough, let's assume it's same, it's pretty safe. Then you can say, hey, my delta F on this small element divided by the delta area, that's your pressure on that particular location, particular element. Okay, that's the fundamental of calculus. Okay, we deal with infinitely small stuff. Okay, then your life is easy if it's infinitely small, it's uniform. So no fancy functions, whatever is linear there. Okay, so be careful. If it's non-uniform problem like this, your local pressure, you have to take a derivative to calculate. Okay, but if it's the uniform pressure problems, easy. P equal to F divided by area. Okay. We will go through this more detail. There's a big subject, a big topic in the textbook about the surface force, surface pressure, how to calculate the pressure on an inclined surface. So we will reach that later. Okay. But now this is the introduction for the pressure. Okay. Okay, pressure is a scalar. Okay, remember this, pressure is not a vector. Okay, force is a vector. Okay, pressure is not. Okay, actually, you probably don't know area is a vector. Okay, a scalar times in vector become a vector, which is a force. Okay, so scalar means it only has value. Okay, there's no direction. You are talking about direction, it's a force. Then it has to times the area. Area has a normal direction, then gives the force a direction eventually when the area times the pressure. Okay, pressure is a scalar. Okay, there are a couple pressure commonly used. Okay, absolute pressure versus gauge pressure. Okay. Commonly used in the industry. Sometimes we use absolute pressure, some of the application. More application, we use gauge pressure. Okay, what does that mean? Okay, pressure is a scalar. So if you talk about absolute pressure, then you have a minimum zero. Is vacuum. Okay, so just like a temperature, if you use K, you have the absolute zero temperature, right? 0K. That's a minimum you can get, at least as a human being we can understand. Okay, that's the minimum. When the particle is absolutely no movement, the temperature is the minimum zero. Okay, same thing for the pressure. If there's nothing there, like in the vacuum, in the vast space, in the universe, the vacuum, there's zero pressure there. Okay, but then there's no more less pressure. Zero is the minimum. Okay, so then everything built on this absolute zero. Okay, for example, atmosphere. You don't feel anything when you sit in the room like that, but you're actually under tremendous amount of pressure. Alien might not be survived on Earth because of that. Maybe they're not used to it. Okay, you're used to it. You start from the first day, you feel the pressure, so you don't feel anything, but you're actually under tremendous amount. You know what's the value actually you're under the pressure? It's 14.7 psi, right? That's that number probably more familiar to you, right? Is that right? Atmospheric pressure, 14.7 psi. You are under that much pressure. And for SI system is 101325, about that Pascal. Okay, so 100,000 Pascal. It's about 113 millibar. Hey, when you weather channel, when you watch weather channel, they talk about hurricane. They always say, hey, hurricane, low pressure. What is the pressure value? They use millibar, right? Okay, millibar is an SI unit. It's Pascal divided by 100. Okay, okay, that make it a little bit, number a little bit smaller. It's a millibar. Okay, 1013, that's the atmospheric pressure in millibar. So what is the pressure Hurricane Laura last time? Do you remember? It's less than 1,000, right? I think probably most of you remember. It's less than 1,000. Lower pressure, it's bad. Hurricane center has lower pressure than atmosphere. 930 maybe. It's a strong monster hurricane, you know. Pressure could be below 950. Everything below 950 is dangerous. Okay, in millibar. So these are the atmosphere. So what I try to say is, hey, if you use absolute pressure, PABS for atmosphere is not zero. You actually is 101,325 Pascal. But you don't feel anything under this value, okay, under this pressure. You don't feel it. So seems like all the engineering practices on Earth, at least for now, maybe if in the future on Mars or Moon or whatever, okay? But and for right now, you're on Earth. So why not, hey, if we don't feel anything, why not we set this at 0? Okay, then we introduce the gauge pressure system. So at the gauge and atmosphere, we set it equal to 0. Okay, we reference the atmospheric pressure as 0. Okay, so everything, any pressure you can feel, there will be a positive gauge pressure. Okay, so that means it's above, it's greater than the atmospheric pressure. Okay, then there will be negative. Okay, it could be negative some pressure value. That means the pressure is lower than atmospheric pressure. Okay, that makes sense, everybody? So I think most of the industrial application you see here, okay, you use a gauge pressure system because it's convenient. This is a convenient, right? It's easy. Everything atmospheric pressure, it becomes 0 in the calculation. You want to see more zeros. Make your life easier, right? In the calculation. That's most of the industry application you see here, around here, use this, except some of the application in refrigeration system. They need to read the absolute pressure. Okay, I know. Still, we still can work with the gauge pressure, but sometimes the pressure, the people maybe don't want to see a lot of the negative pressure, so that's why they use absolute system. Okay, but keep in mind, so when you talk about pressure, you need to know, from now on, you need to know we are in the gauge system or absolute system. Okay, it's totally different in the calculation. Okay, so if you use absolute pressure system, it's not possible to be negative, right? Do you agree? Because you have a low minimum 0 there, okay? At least maybe in the black hole or something, you know, I don't know. I don't understand. I cannot feel, right? But in the world there, you can feel, hey, 0 is the minimum, okay? But if you use the gauge system, it can be positive or can be negative. Okay, but what is the minimum pressure value if you use gauge system? If you use gauge pressure?
Negative 14.7.
Negative 14.7 psi. In Pascal is negative 101,000. That's your minimum bound. Okay, right? It's not possible to get the negative 20 psi. Okay, sometimes you did some calculation wrong. It turned out to be a negative 20. It's possible. I'm telling you, it's possible. You know, in the calculation, you could make a mistake, right? But it's a good habit to check it, to make sure to check it's reasonable. If you write a technical report to your boss, say negative 20 psi, that could be your career-ending report. Don't make those foolish mistakes, right? Okay, you know that the minimum bound, it's not possible to exceed the negative 14.7 psi. Okay, or negative 101,000 Pascal. Okay. Okay. Any questions so far? That good? Clear? Crystal clear? Okay. If you're crystal clear, okay, that's good. Okay, let's introduce the first principle of hydrostatics. Pascal's law. Oh no. Yeah, Pascal's law. Pascal's principle. Okay, I think that the section in the textbook talks about that. I don't remember the exactly wording. Maybe I can find. Let me see. The Pascal's principle. It's okay. I can just tell you what I understand. Okay, so what it says is this: if you have a container, let's say I have a container here, it's filled with liquid. Okay. So first of all, let me ask you this. Do you understand the pressure along this surface of water? Are they the same or not? You have a tank or whatever container. It's filled with water. On any given location on the tank wall, first of all, I want you to have the common sense here, okay? Is the pressure value same or not? Anybody? I have a point here, point A, point B. Is the pressure the same on A and B? Where's the pressure coming from? The pressure is coming from the water, right? Filled in the tank, okay? If you talk about atmosphere, the same, inside and outside both have atmospheric pressure, so they cancel it out. So basically the pressure reading A and B is from the liquid filled in the tank, okay? Are they the same, first of all? That's your high school physics, right?
No.
Why? Why not? Again, see, you answer my question with a no, but without have a justification there. Okay.
Maybe because it's a different height between the 2
Yes,
points.
exactly. We follow the equation. The pressure, you calculate pressure is rho gh. Is that right? These 2 points I follow the equation. Rho g is a constant, doesn't matter. H, if H changes, pressure changes. A and B are different. We'll talk about this thing later in the chapter, but I just want to mention it here for everybody fully understand the problem itself, okay? Pressure is not same if the elevation, if the depth is not the same, okay? So you have different, unless you have 2 points next to each other, they have the same elevation. Well, sure, they have the same pressure if they have the same elevation. Okay, so Pascal's law never say the pressure is the same inside of the container. It says this: if you're adding a pressure, I'm adding a pressure on one surface of the fluid. Okay, it's opening here. I'm pushing the opening. I'm adding a pressure delta P into the system. Then what will happen? What will happen is this added pressure delta P will be transmitted 100%, will be transmitted to everywhere inside of this container. It's immediately everywhere will feel this added pressure delta P. Okay, that's Pascal's law. It never said that, hey, PA and PB will be the same. No, pressure is always different. But PA will feel you have a plus delta P. PB, okay, this is the B. PB also become PB plus delta P. Okay, PC is also PC plus delta P. Whatever original pressure is still there. Okay, then this added pressure delta P will be felt everywhere inside the container. Okay, this is the Pascal's law. Is that understandable? Did that create any confusion here? Well, it's a small class here. We have 15 here, right? Well, I want everybody on the same page. Okay, that understandable? That's a pressure transmission law, basically. It means that it's not really the pressure transmitted, it's the added pressure. If you let the pressure change, okay, the added pressure or remove the pressure, okay, the delta P will be filled immediately, okay, and everywhere, there's no loss for that delta P. Everywhere will feel it 100%. Okay. This is the ancient principle. Okay, Pascal just make it into a sentence. Okay, no big deal for him. Okay, put his name on it, seems like a big deal of him. No, this is 5,000 years principle. Without this, Egyptians won't be able to make the pyramid. Okay, hydraulic machine. This is the fundamental of the hydraulic machine. You add a little pressure on one side, the other side will feel the same pressure. But let me draw something fancy here. Okay, not fancy, useful. Okay. Okay, let's say you have a system like this. Hydraulic machine. Do you know hydraulic machine? Some of you more practical, you know, hands-on, you played with hydraulic machine before, right? I have two pistons here. It's a hydraulic jack. Maybe I put a lever here. Okay, you can pressurize the piston. Okay, what's the fancy part of this device is, okay, I have a big surface area here in this side, then the surface area here. Okay, so I push it down here in the small side. Okay, I give a very reasonable force that I can handle. Okay, so you have a delta P. I'm adding a little bit pressure to this hydraulic fluid. What happened to this delta P added to the system? Hey, follow the Pascal's law I just said. This delta P will be felt immediately everywhere inside of this container, including this surface. You also feel a delta P pushing up. Is that right? Okay. So what really matters is the force, right? You measure force. You know, forces actually can do the work, right? So force. So how do you calculate the force? That's the uniform pressure on the both surface. So that added pressure times the area is the force you actually created on the larger side. In the small side, hey, it's small delta, a small area, A1, A2. So you add a reasonable amount of force, then you can add, everybody can add. divided by area, it becomes a small delta P. But this delta P transmitted back to this side with a bigger area, actually it creates a bigger force. Okay, that's so fancy. Okay, so force seems like it's not balanced. The people were always confused by the force balance with the energy balance. They will think about, hey, energy has to be balanced. How can I create force? No, force, you can, yes, you can create a force from nowhere. Okay, okay, that's the Pascal's law. That's the hydraulic machine. That's the 5,000 years, even more, okay, principle. People all noted, discovered that a long time ago, but we, you know, used it for a long, long, long time, okay. Building giant structures, you definitely had, I think all the Egyptians had definitely used this hydraulic machine to lift those big rocks, right? Otherwise, it's not possible. Okay, so, but Pascal just make it into a sentence, conclude it, okay. That's the, I think that's the first principle we want to introduce. Okay, the other example in the textbook, we can go through that. Actually, that's it's a hydraulic jack, right? Let me see. It's very, very useful principle. Okay, go through that. We'll have about more than 10 minutes. Let's go through that. It's not a difficult problem, but okay, it is a hydraulic jack. We have a fluid inside. It's a fluid part. You have two surfaces. Okay, one surface you have a piston. You connect it to a lever. Okay, the dimensions. This is at the hinge. The lever, you know, rotate about the hinge. Okay, then this is a piston, it pushed down, but in the middle. The length of the lever, I think this is a 30 centimeter. Okay, this is 3 centimeters between the piston and the hinge on the wall. Okay, the other side, okay, the diameter D1 is what, small, I think. 1.5 centimeter, okay. It's a very, very pocket-sized device, very small. D2 is 5 centimeter. Yeah, 5 centimeter, okay. So when you push down with a force 100 Newton, okay, 100 Newton force pushing down for this pocket-sized device, refer to the textbook, okay. See what kind of force it can lift, okay. A small hydraulic. Any question? Bear with my drawing. My drawing is terrible, I know. Okay, we can answer it. Any part is not clear. 30 centimeter and a 3 centimeter. Its total length is 33 centimeter. Okay. The two pistons, 1.5 centimeter for diameter, which is a little bit more than ½ inch, right? This is 5 centimeters. The other end is 2 inch. Okay, very small device. Okay, imagine that's tiny. Okay, only thing is the lever, maybe foldable, those lever. Lever is like a 30 centimeter long, 33 actually. 33 is about 10 inch, right? 12 inch maybe. No, 12 inch, yeah, for the lever, okay? So you push down, you push the piston here, push down at the end of the lever, you give it a little bit moment, right? So it's a little bit torque, so it's easier to put, it can create a little bit more force. So 100 Newton force. Do you know what 100 Newton? 100 Newton equal to how many pounds? Anybody? Do you want to Google it for me? Newton to pound, 100 Newton. I just want to know 100 Newton, you know, I don't have a feel what is really 100 Newton. $20, right? Yeah. About 20 points, is that right?
Yeah, 22.5.
22.5 pounds, okay. Can you push 22.5 pounds? I can push 200 pounds, maybe 100 pounds. Okay, 22.5 pounds is a piece of cake for everybody, even for the kids. Okay, so everybody can produce that 22-pound force here. Okay, 100 Newton. Okay, see how much it can actually lift. Okay, so this is the problem. So how do we do this? I think many of you know how to do it already, but I just want to go through the standard process again. So you draw free body diagram. It's a static problem, right? Free body diagram always for the lever, because you want to calculate the force on the first piston, the small piston. Okay, so the lever, you detach it from the wall, you replace it by the two supporting force, but doesn't matter in this problem. We don't need to use X, Y, but I still like to draw on it. Okay, so this is the force 100 Newton, F1, 100 Newton on the one end. Okay, here you apply a force you want to calculate, right? In the in the smaller piston. Is that right? Okay, action reaction, right? You detach the piston from the fluid. So basically, I should say this. How about this? Reaction should be going upward. Make it right, okay? Let's say this is the FH, the people in the handle. This is F1. F1 is on the small piston. Is that right? Is my drawing understandable here? The free body diagram? Okay, this IXRY, this is the hinge. The lever actually rotates about the hinge. Okay, F1 is the first piston here. So the distance here is 3 centimeter, and the distance between F1 and here is 30 centimeter. Can you draw the free body diagram like this? Independently? Okay, critical, that's. IXRY, don't worry, because actually when you draw the free body diagram, you have to detach the lever from the wall. If you detach it, the hinge usually replaced by a two unknown force, IX and RY. Okay, you don't know the direction, but they have a component, so you can easily put it on there. In some problem, you need IX and RY, but in this problem, you don't. The reason you don't is you're gonna use the moment equation instead of a force balance. The moment equation is the moment about this point. So this IX and RY have no moment about the hinge. Okay, so it's okay. It's totally negligible in this problem, but it's safe to write it on the drawing. Make it a correct free body diagram. Okay. Any question on this drawing? I want to make in the last quiz. Some of you take a point or take a point 1.5, take a half point. That's because the drawing is not 100% correct. Some of you miss the arrow for the force. Some of you look the arrow doesn't look like verticals, and if it's not 100% correct, I'm not satisfied. I take some point off. Okay.
Professor?
Yeah.
What's the units on F of H?
100 Newton.
Thanks.
That's a force you push down.
Yes, sir. Thank you.
You're welcome. Yeah, it's Newton. Okay. It's okay. You want to use 22.5 PS pound. 100 is easier for the calculation, right? Okay. So the equation. Now this is a good free body diagram. Okay. You detach the lever from the piston. With a piston force here. You detach a lever from the wall. You have a supporting force IXRY here. Okay, it's complete. It's good. 100% correct. Okay. So now the equation you want to write, it's not summation of force equal to 0 anymore. In this problem, is rotating problem. Okay. Remember, if it's a rotating problem, you're going to choose the moment equation instead of force equations. Okay. Moment about O point. Give me the location for the hinge. I put the letter O here. Okay. That tells me that's a moment about the O point. Okay, equals 0. That's the direction. So how many minutes I have? 5 minutes. Okay, I need to be a little bit faster here. Okay, is that good, everybody? The moment equation, I want you to write like this: summation of moment equal to 0. It could be 1 moment, it could be 2 moments. So that's why I have the summation here. That's the rule of thumb, principle of drawing into statics, right? After draw three-body diagram, you write down the equation, either force balance or moment balance, depend on rotating or not, okay? Now expand this equation. How many moments we have in this problem? About O. Just look at the free body diagram. Don't look at anything else. Look at the free body diagram. How many moments? And what are they?
2.
2 moments, okay? One from the force you apply FH, the other is from the supporting force on the piston, right? So which one is the positive moment? Do you know? Is clockwise positive or counterclockwise positive? Rotation
Is
by
it
convention.
clockwise?
Counterclockwise is positive. Okay, so here, which rotation is counterclockwise? I think is FH, right? That's counterclockwise. So this is positive. FH times 33, 0.33 meter, minus the other F1 is clockwise, right? F1 times 0.03 meter equals 0. I still be good habit to put a meter instead of centimeter. Okay, in this problem doesn't matter, but it will be safe to do that. Okay, so can I calculate the F1? FH is 100, so this is the 100, right? So F1 equals what? Anybody give me a 1100, I think. 11 times, right? For the 0.33 and the 0.03. So it should be 1100 Newton on F1. Is that right? Double check with me. I didn't do any calculation. I just estimated, right? 11 times longer. So the arm is 11 times longer there. So what is the pressure then? P1. So added pressure, delta P1. I think I like to use delta P1 because that's the added pressure on one, right? So it's 1100 divided by the area, right? Quarter pi d squared. The d is 0.015 squared. Okay, so that added pressure on one will be equals to added pressure on P2. Okay, I've jumped a little bit, but I don't know the force on P2. F2 divided by quarter, that's Pascal's principle here, times 0.05 square. Okay, I'm out of space here. I don't want to use another page. Okay, is that right? Hey, I jumped a little bit. I skipped a little bit here. Is that too fast? Any questions? Pascal's principle, that means the added pressure will be felt everywhere inside this fluid. This is a hydraulic machine, so this is fluid, right? It's raging the fluid. So surface 2 also felt the added pressure on surface 1, which is this equation. Is that right? You don't have to write the notes. I can post this later, you know. Yes, you can write. I post later, you know, if you want to keep it right now, yeah, go ahead. But try to understand it. I have 1 minute here. Is that the Pascal's principle? Delta P1 equals to delta P2. The added pressure is the same everywhere inside this container. Okay, but the added pressure will be force divided by the area. Will be equivalent to the force, so that we can calculate the F2 actually. I think F2 equals, I just directly give you the answer. How about that? F2 equals to 12,200 Newton. Okay. So it can actually lift a lot. Okay. How's that? It's more than 2,000 pounds. Okay. It's more than 2,000 pounds. Actually, it can create the force on the other end. Okay. More than 2,000. I don't think any of you here can lift 2,000 pounds, right? It's a small vehicle. Well, Arthur, can you? No, I don't think so. You can probably lift 300.
No, I ain't lifting no 2,000 pounds.
Not 2,000 pounds at least. Okay. So, hey, it's a pocket device, such a small pocket device. Okay. Use the hydraulic principle here. You can lift a lot of stuff. They lift a car, basically. Okay. I guess I'm out of time here. Okay. Let's talk about it next time. Any question here? Okay. So that's the first principle of statics, Pascal's principle.
Good weekend.
Have a good weekend. Okay. Hey, stay warm, guys. It's pretty unusual to see a hard freeze like this. You know,
Shorts and t-shirt
yeah.
kind of weather.
I'm trying. You know, when I move here, I'm trying to escape the cold freeze. You know, from the north. But eventually, I end up still have a cold freeze here. It's a strange year.
Oh, it's just getting started.
It's getting started. Okay. 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 Have a good
Have a
weekend.
good weekend.
Happy Mardi Gras.